Picture this: a world of rust-red deserts, towering cliffs, and valleys so vast they dwarf the Grand Canyon. But what if I told you that Mars, the barren planet we see today, might once have been home to oceans as deep and mysterious as those on Earth? The evidence is etched into its surface, in formations so strikingly similar to Earth's ocean floors that scientists can't help but wonder, are we looking at the remnants of an ancient Martian sea? This isn't just science fiction. It's a real, unfolding mystery that could rewrite everything we know about the Red Planet. Take a closer look at those alien landscapes, and you'll start to see the uncanny parallels. Gigantic canyons that resemble underwater trenches, sprawling plains that mirror abyssal floors, and strange, winding ridges that look like fossilized shorelines. These aren't random quirks of geology, they're clues, hints that Mars might have once been a world of water, teeming with possibilities. And if that's true, what else might be hiding in those long, dried depths? Could there have been life thriving in those ancient Martian oceans, just as it does in ours? The questions alone are enough to send chills down your spine. That's why today, we're embarking on a journey across 24 of Mars' most puzzling terrains, places where the line between Earth and the cosmos blurs. We'll explore towering plateaus that mimic underwater volcanoes, cracked basins that look like dried-up seabeds, and eerie formations that defy easy explanation. Each one holds a piece of the puzzle, a fragment of a story that could change how we see not just Mars, but our own planet's place in the universe. By the time we're done, you'll never look at the Red Planet the same way again. So buckle up, because what we're about to uncover might just bend your understanding of reality itself. Let's start with Valles Marineris, a colossal scar across the face of Mars that makes Earth's Grand Canyon look like a mere scratch. Stretching over 4,000 kilometers, nearly the width of the United States, this Martian mega-canyon isn't just big. Its very structure whispers secrets of the planet's watery past. Look closely and you'll see layered cliffs, winding channels, and branching tributaries that mirror Earth's submarine canyons, like the Monterey Canyon beneath the Pacific. On our planet, these underwater chasms are carved by powerful currents, sediment-laden flows that rush down continental shelves like rivers in the deep. So when we see the same patterns on Mars, it's hard not to ask, were ancient floods or even ocean currents once at work here? The walls of Valles Marineris tell a story of erosion, but not the kind caused by wind or dry landslides alone. The terraced layers, the smooth slopes, they look like the handiwork of water, patiently shaping the landscape over eons. Some researchers even suggest this canyon might have once been part of a much larger network, a drainage system for an ancient Martian sea. Imagine, if you will, a time when Valles Marineris wasn't a dry, sun-baked rift, but a submerged channel where water surged, carrying sediment and carving its way through the rock. The scale alone is staggering, depths reaching 7 kilometers in places, enough to drown Mount Everest with room to spare. But here's where it gets even more intriguing. On Earth, submarine canyons are hotspots for life, where nutrient-rich waters fuel entire ecosystems in the eternal dark. If Mars once had similar conditions, could those vanished waters have harbored life too? We may not have proof yet, but the resemblance is more than superficial. Every groove, every curve in Valles Marineris seems to echo Earth's submarine landscapes, as if the two worlds were shaped by the same forces. That's the real mystery, not just whether Mars had water, but whether its past was as dynamic and alive as our own oceans. And if so, what other secrets might still be buried in those rust-colored cliffs? Now shift your gaze to Aram chaos, a fractured, jumbled expanse on Mars that looks like a puzzle smashed to pieces. This is what scientists call chaos terrain, and it's one of the most bizarre landscapes in the solar system. Towering blocks of rock, some as wide as cities, sit scattered across the surface like debris from a planetary explosion. But here's the twist. These shattered formations bear an eerie resemblance to Earth's hydrothermal vent fields, those deep-sea oases where superheated, mineral-rich water bursts from the ocean floor. On our planet, these vents are teeming with life bacteria, tube worms, and other organisms thriving in total darkness, fueled by chemistry rather than sunlight. So when we see Mars' chaos terrain, it's impossible not to wonder, could this shattered landscape have once been a hub of hydrothermal activity? And if so, did life ever cling to its steamy fractures? The similarities are too striking to ignore. On Earth, hydrothermal vents form where tectonic activity or volcanic heat cracks the seafloor, allowing water to seep down, get superheated, and rise again in billowing plumes. Over time, this process can create jagged, mineral-crusted towers and maze-like fissures, almost like a mirror image of Aram chaos. And just as Earth's vents are lined with iron, sulfur, and silica deposits, Mars' chaos regions are strewn with hematite and other minerals that typically form in watery, high-temperature environments. It's as if someone took a snapshot of our ocean floors and projected it onto Mars but drained all the water away. That's where the real fascination lies. Hydrothermal vents aren't just geological curiosities, they're crucibles for life. Even in Earth's most hostile depths, these systems sustain entire ecosystems, proving that life can flourish without sunlight, using nothing but heat and chemistry. If Mars once had similar vents, could tiny, resilient organisms have emerged in their shadows? We may never find definitive proof, but the ingredients were there: liquid water, heat, and a buffet of minerals. Some researchers even speculate that Mars' chaos terrains could preserve microfossils, locked away in their rusty rocks like ancient time capsules. But the mystery goes deeper. Unlike Earth, Mars lacks the tectonic forces that usually drive hydrothermal activity here. So what could have cracked its crust so violently? One theory points to catastrophic floods, perhaps massive underground reservoirs bursting free, collapsing the terrain as water erupted to the surface. Another suggests ancient volcanic heat melting ice buried below, turning the ground into a slurry of mud and rock. Whatever the cause, the result is a landscape that feels both familiar and alien, a place where Mars' past seems to reach out and whisper clues about its lost potential. And if we're right about those whispers, the implications are staggering. A second genesis, a shadow biosphere, or perhaps even the first evidence that life isn't unique to Earth after all. Now let's turn our attention to Eberswalda crater, where Mars serves up one of its most compelling geological mysteries, a delta that wouldn't look out of place on Earth. Picture the Mississippi River fanning out into the Gulf of Mexico, or the Nile spreading its sediment across the Mediterranean. That's exactly what we see here, but on an alien world. The Eberswalda Delta is a sprawling, fan-shaped deposit of layered rock, its branching channels frozen in time, as if someone pressed pause on a river's flow millions of years ago. On Earth, deltas like this form over centuries, built grain by grain as flowing water slows down and dumps its sediment into a larger body of water. So when we find the same intricate patterns on Mars, it's not just a coincidence, it's a smoking gun. This isn't some vague resemblance. The Eberswalda Delta has all the hallmarks of a water-carved feature, from its finely layered deposits to the unmistakable way its channels split and reconnect, just like Earth's river deltas. Scientists estimate it would have taken thousands, maybe even millions, of years of steady liquid water to create something this detailed. That's a game changer. Mars wasn't just wet for a fleeting moment. It had persistent rivers, lakes, or even seas, stable enough to shape landscapes over geologic time. And if water stuck around that long, what else might have flourished in it? On Earth, deltas are biodiversity hotspots, where nutrients pile up and life thrives in the mix of fresh and salt water. Could the same have been true on Mars? The implications are staggering. Deltas don't just hint at water, they're natural archives, preserving layers of sediment that might contain clues about Mars' ancient environment. Imagine slicing into those layers and finding organic material or even fossilized microbes. It's not as far-fetched as it sounds. On Earth, river deltas bury and protect evidence of life all the time. The same could have happened on Mars, sealing away traces of whatever might have lived there in its watery prime. But here's the twist: Mars doesn't make it easy. Unlike Earth, where plate tectonics constantly refresh the surface, Mars is a frozen museum. Its deltas aren't buried under new layers, they're exposed, battered by dust storms and radiation. Yet somehow, Eberswalda's delta survived, almost as if it's waiting for us to decode its secrets. That's why missions like NASA's Perseverance rover are so crucial. By studying these formations up close, we're not just reading Mars' history, we're asking one of the biggest questions of all. If life ever got started there, could its echoes still be hiding in the rust-colored sands of a long-dead river delta? Heading toward Mars' polar regions, the landscape transforms into something straight out of an abstract painting: vast plains fractured into intricate polygonal patterns, like a colossal honeycomb etched into the planet's skin. These aren't random cracks, they're near-perfect geometric shapes, some as large as a city block, others as small as a dining table, all tessellating across the frozen ground. And here's the kicker: they look identical to the polygonal networks found in Earth's Arctic tundra, where icy soil contracts and expands with the seasons, fracturing the ground into jagged, interlocking pieces. On our planet, these patterns are textbook signs of freeze-thaw cycles: water seeping into soil, freezing into ice wedges, then expanding to pry the Earth apart like a natural crowbar. So when we spot the same shapes on Mars, it's not just a curious resemblance. It's a frozen fingerprint of a time when water wasn't just present on the red planet. It was shifting, cycling, and actively shaping the terrain. But Mars doesn't do anything halfway. These polygons aren't just superficial scratches. Some trenches between them plunge several meters deep, suggesting relentless expansion over centuries or even millennia. On Earth, that kind of sustained cracking requires a delicate dance of climate seasons: cold enough to freeze groundwater, but warm enough to let it thaw repeatedly. So what does that imply for Mars? Either the planet once had a climate capable of seasonal swings, or some other process, like the slow sublimation of buried ice, mimicked those cycles on a geologic timescale. Either way, these polygons aren't just relics. They're time capsules preserving a record of environmental changes that might have once made Mars shockingly Earth-like. And that's where things get tantalizing. In Earth's permafrost, these ice wedge networks aren't just geological oddities, they're natural freezers, preserving ancient organic material like woolly mammoth DNA or prehistoric plant matter for tens of thousands of years. If Mars polygons formed under similar conditions, could they have trapped and protected traces of life? Imagine microscopic organisms, if they ever existed, locked in icy stasis beneath those geometric cracks, shielded from radiation and decay. It's a long shot, but not impossible. Recent studies of Earth's permafrost have found microbes thriving in ice wedges, surviving in a state of suspended animation for millennia. Could Mars' polygons be hiding similar surprises? The answer might lie in the chemistry. On Earth, freeze-thaw cycles concentrate salts and organic compounds along the edges of ice wedges, creating tiny oases of reactivity even in frozen soil. Mars' polygons show similar mineral concentrations, sulfates, chlorides, and other salts that, on Earth, act as antifreeze, keeping microscopic pockets of water liquid even in sub-zero temperatures. That's the holy grail. Liquid water, however fleeting, could have provided a refuge for Martian life if it ever existed. And if those briny pockets lingered long enough, they might have left behind chemical fossils, subtle traces of biological activity frozen in the salt. Yet Mars throws us a curveball. Unlike Earth, where polygons form near the surface, some Martian versions appear to originate deep underground, suggesting ancient ice layers that were buried, then exposed by erosion. That adds another layer of mystery. Did these patterns form under a thicker atmosphere when Mars was warmer and wetter, or are they evidence of underground aquifers freezing and thawing in isolation? Each possibility paints a different picture of Mars' past, one where water wasn't just a fleeting visitor, but a persistent force sculpting the planet from the surface down to its hidden depths. So the next time you see those geometric cracks in satellite images, remember, they're not just fractures, they're a planetary diary written in ice and soil, waiting for us to decode its pages. And if we're right about what they're telling us, the story might be far richer and far more alive than we ever imagined. Rising from the heart of Gale crater, Mount Sharp stands like a natural library of Mars history, its slopes stacked with hundreds of layered rock formations, each one a potential chapter in the planet's enigmatic past. These aren't just random piles of rubble. They're sedimentary layers meticulously deposited over eons, and they bear an uncanny resemblance to the strata found on Earth's ocean floors. Picture the Grand Canyon, but instead of being carved by wind and rain, imagine its layers laid down by ancient lakes or seas, their minerals whispering secrets about the environment that formed them. That's precisely what NASA, a Curiosity rover, discovered as it climbed Mount Sharp's foothills, a geological storybook with pages made of stone. What makes these layers so compelling is their composition. Embedded within them are minerals like hematite, a rusty iron oxide that on Earth often forms in the presence of water. Then there's clay, which typically settles in calm, wet environments, and sulfate salts, which hint at evaporating bodies of water, like a Martian version of the Dead Sea. Together, these minerals paint a picture of a world that cycled between wet and dry, perhaps over millions of years. It's not just proof that water existed, it's evidence that Mars' climate was dynamic, shifting between eras of flooding and drought like a planet struggling to hold onto its lifeblood. But here's where the mystery deepens. On Earth, sedimentary layers are like time capsules. They trap fossils, preserve ripple marks from ancient waves, even capture raindrop impressions from storms that fell a billion years ago. If Mars' strata formed underwater, could they hold similar relics? Curiosity hasn't found fossils yet, but it has detected organic molecules, the building blocks of life, nestled in these rocks. That doesn't mean life existed, but it does mean the ingredients were there, mixed into the same kind of muddy deposits where, on Earth, microbes thrive. The real revelation, though, is in the layers themselves. Some are thick and coarse, suggesting fast-moving floods or river deltas dumping sediment in violent pulses. Others are thin and delicate, likely laid down in still, shallow waters, perhaps the bed of a long-vanished lake. This variation isn't random. It's a record of environmental changes, like a planetary mood ring shifting from blue to red as Mars dried up. And just like Earth's oceanic strata, which preserve traces of asteroid impacts and climate shifts, Mount Sharp's layers might hide cosmic events, volcanic eruptions, meteor strikes, or even the moment Mars' atmosphere thinned, turning the planet into a desert. Yet the most tantalizing question remains, why here Gale crater wasn't just a passive basin. It was a hub, a place where water pooled, evaporated, and pooled again, leaving behind a layered testament to its comings and goings. That kind of persistence is rare, even on Earth. Most sedimentary environments are wiped clean by erosion or tectonics, but Mars, with its frozen geology, preserved these layers like a time machine. Every new stratum curiosity examines is another clue, another piece of the puzzle. And if we're lucky, somewhere in those rust-colored rocks, there might just be the one clue we're all waiting for, proof that Earth wasn't the only world where water wrote the story of life. Now, let's explore one of Mars' most deceptive landscapes, ridges that snake across the surface like raised scars, twisting and branching in patterns that look eerily familiar. These aren't mountains or cracks. They're inverted channels, the ghosts of ancient rivers that once flowed freely across the red planet. Here's how it works. When water carves a riverbed, it often leaves behind coarse sediment, pebbles, sand, and minerals that's tougher than the surrounding terrain. Over time, wind and erosion wear away the softer rock, but the hardened river deposits resist, leaving the old channel standing proud as a raised ridge. It's like nature's version of a negative image, where the valleys become peaks and the rivers become fossilized skeletons of themselves. And Mars isn't the only place this happens. On Earth, places like Utah's San Rafael swell showcase the same phenomenon, sinuous ridges of sandstone that were once riverbeds, now towering above the eroded plains. The difference, Earth's inverted channels are rare, preserved only in the most stable environments. On Mars, they're everywhere, crisscrossing the landscape like a global network of ancient waterways. That's the first clue that water didn't just visit Mars, it stayed, shaping the planet for far longer than we once thought. Some of these ridges stretch for hundreds of kilometers, with branching tributaries so intricate they could have been lifted straight from a geography textbook. But the real magic lies in what these fossil rivers imply. On Earth, rivers don't form overnight. They need steady precipitation, groundwater recharge, or melting ice to keep flowing season after season. Mars' inverted channels suggest the same kind of persistence, not flash floods or fleeting bursts of water, but sustained flow over decades, centuries, or even millennia. That's a game changer. If water stuck around that long, the planet's surface could have been habitable for far longer than we imagined, offering a stable environment for life to take hold. And here's where the mystery thickens. Some of these ridges contain minerals like silica, which on Earth forms in hot springs or hydrothermal systems, places teeming with microbial life. Others are lined with iron-rich clays that act like chemical sponges, trapping and preserving organic material. It's as if Mars' rivers didn't just vanish, they left behind a breadcrumb trail of their most life-friendly spots. Yet the biggest question remains unanswered. Why did these rivers invert in the first place? On Earth, it's usually because the riverbeds were laced with volcanic ash or cement-like minerals that hardened over time. But Mars lacks active volcanoes, so what armored its rivers against erosion? Some scientists point to groundwater percolating up, depositing minerals that turned the riverbeds to stone. Others suggest the planet's thin atmosphere allowed brutal winds to strip the landscape bare, leaving only the toughest deposits behind. Either way, these ridges aren't just relics, they're time capsules, holding secrets about Mars' wettest, most Earth-like era. And if we're lucky, they might just hold something even more precious, proof that the red planet's rivers didn't just flow, they thrived. Deep within Mars' northern plains lies a bizarre landscape of lumpy, dome-shaped mounds, Planitia, a region dotted with formations that look like they've been squeezed up from beneath the planet's crust. These aren't your typical volcanoes spewing molten rock. Instead, they bear an uncanny resemblance to Earth's mud volcanoes, those gurgling, sludge-filled vents where water, gas, and sediment erupt in slow-motion geysers. On our planet, these seeps are often found on ocean floors or in wetlands, places where pressure forces waterlogged mud upward, creating bubbling pools and cone-shaped hills. So when we see nearly identical structures on Mars, it's hard not to wonder, was this once a place where the red planet's hidden waters oozed to the surface, carrying secrets from its depths? The parallels are striking. Earth's mud volcanoes form when underground water mixes with fine sediment, creating a slurry that's lighter than the surrounding rock. Trapped gases like methane or carbon dioxide build pressure until the mixture bursts through cracks, piling up layer by layer into mounds that can tower hundreds of feet tall. On Mars, the mounds of Acidalia Planitia show the same telltale features: flattened tops, concentric rings, and even what appear to be dried up flows of mud stretching across the plains. Some scientists argue these could be the fossilized remains of ancient eruptions, their once soupy interiors long since hardened into rock. But here's where it gets really interesting. On Earth, mud volcanoes aren't just geological oddities, they're biological hotspots. The methane and other chemicals spewing from these seeps feed entire ecosystems of microbes, creatures that thrive without sunlight, drawing energy from the chemical soup instead. Around submarine mud volcanoes, entire colonies of tube worms, clams, and bacteria cluster in the dark, living proof that life can flourish in the most unlikely places. So if Mars had similar seeps, could they have been oases for alien microbes? The ingredients were there: liquid water, organic molecules, and a steady supply of energy-rich chemicals. It's not hard to imagine tiny organisms eking out an existence in the damp sludge, hidden beneath a thin crust of dried mud. The implications are electrifying. Mud volcanoes don't just hint at water, they suggest a dynamic, chemically active environment, one where life could have found refuge even as Mars' surface dried up. Unlike flash floods or temporary lakes, these seeps might have offered stability, bubbling away for thousands of years in a slow but steady cycle. That's a big deal. Life, if it ever existed on Mars, would have needed more than just a single wet moment. It would have needed time and consistency, exactly the kind of conditions mud volcanoes could provide. And there's another tantalizing clue. Many of Mars' mud-like mounds are surrounded by mineral deposits, sulfates, carbonates, and clays that on Earth often form in the presence of microbial activity. These minerals don't prove life existed, but they do mark spots where the chemistry was ripe for it. Future rovers could target these areas, drilling into the hardened mud to search for microscopic textures or chemical signatures that whisper of ancient biology. Yet mysteries remain. Without active plate tectonics or the same kind of underground gas buildup that drives Earth's mud volcanoes, how did Mars' seeps form? One theory points to buried ice melting under pressure and mixing with soil to create a slippery slurry. Another suggests thawing permafrost, releasing trapped gases that forced mud upward in sluggish eruptions. Whatever the cause, the result is a landscape that feels both alien and familiar, a place where Mars' hidden wet past might still be written in the dried-up sludge. So the next time you see those odd, pimple-like mounds in satellite images, remember, they're not just bumps on a barren plain. They're potential time capsules, holding clues to a time when Mars wasn't just red and dead, but a world of seeping, bubbling mud, and maybe, just maybe, a haven for life clinging to its last muddy refuge. Descend into the depths of Mars Hella's Basin, and you'll find valleys that defy the planet's dry, wind-swept reputation, twisting channels so perfectly carved, they look like the work of rivers. But these aren't just any rivers. Their steep walls, smooth floors, and braided patterns bear an unmistakable resemblance to Earth's subglacial trenches, the hidden waterways that snake beneath ice sheets like Antarctica's. On our planet, these channels form where meltwater flows beneath miles of ice, its pressure so immense that it carves through rock like a scalpel. So when we spot nearly identical features on Mars, the implication is staggering. This barren world might once have harbored vast ice-covered oceans, with liquid water surging beneath their frozen shells. The evidence doesn't stop at the shape of the valleys. Hellas Basin's trenches are flanked by ridges and grooves that mirror the eskers and drumlins found on Earth landforms created by glacial movement and subglacial floods. Picture Antarctica's hidden Lake Vostok, sealed under 4 kilometers of ice for millions of years, yet still home to liquid water and microbial life. If Mars had similar ice-covered seas, its subglacial valleys could have been conduits for warmth, nutrients, and even geothermal heat, creating sheltered pockets where life might have clung on. The similarities are so precise, it's as if Mars left us a geological cry for attention, shouting, "Look closer, I was once like you, but here's the twist." On Earth, subglacial environments are among the most extreme habitats life can endure, dark, crushing, and isolated. Yet they're also remarkably stable, shielded from surface radiation and temperature swings. If Mars' ice sheets were thick enough, they could have offered the same protection, turning these valleys into potential oases. Imagine a network of pitch-black tunnels, lit only by the faint glow of hydrothermal vents, their walls coated in microbial mats feeding on chemical reactions. It's not science fiction. On Earth, such ecosystems exist in the deep ice of Greenland and Antarctica, where bacteria thrive without sunlight, oxygen, or organic food. The real clincher, Hellas Basin, is one of Mars' lowest points, a natural depression where water and ice would have pooled. Some researchers believe it once held a massive, frozen sea, with subglacial valleys acting like plumbing, funneling meltwater between buried lakes. That's a game changer. Liquid water beneath ice isn't just a fleeting phenomenon. It can persist for eons, even as the surface freezes solid. And if Mars had these stable, watery hideouts, they'd be prime real estate for any hardy organisms trying to survive the planet's descent into dryness. Yet the biggest question remains unanswered. How much heat would Mars have needed to keep those subglacial systems alive? On Earth, geothermal activity and tidal forces from the Moon help sustain subglacial lakes. Mars lacks both, but volcanic activity in its past could have provided the necessary warmth, or perhaps impacts from asteroids temporarily melted the ice, creating transient pockets of habitability. Either way, these valleys aren't just relics of water, they're clues to a world that might have been far more alive and far more hidden than we ever dared to dream. So while Mars' surface today is a museum of dust and rock, its underground past could tell a different story, one of dark, bustling waterways shielded by ice where life might have lurked in the shadows. And if we're right, the next great discovery in the search for extraterrestrial life might not be on the surface at all, but buried deep beneath the rust-colored soil, waiting in the echoes of these ancient, ice-carved valleys. Stretching across Mars' Nili Patera, a sprawling sea of sand dunes ripples like a frozen ocean, each crest and trough sculpted by winds so thin you could barely feel them. Yet these dunes hold a secret. They're almost perfect twins to the underwater sand waves found on Earth's continental shelves, where ocean currents shape the seafloor into rhythmic, flowing patterns. On our planet, these submerged dunes form when water pushes sediment into towering ridges, sometimes hundreds of feet high, marching across the seabed in slow motion. On Mars, the process is eerily similar, except instead of water, It's the planet's whisper-thin atmosphere that does the sculpting, grain by grain, over millennia. But here's where the comparison gets fascinating. Earth's underwater dunes aren't just piles of sand. They're dynamic ecosystems where currents trap nutrients and organic matter, creating hotspots for marine life. Could Mars' dunes have played a similar role? Hidden beneath their wind-swept surfaces, scientists have detected minerals like clays and sulfates, materials that typically form in the presence of water. Some dunes even show signs of ancient hydration, as if they were once damp before Mars' oceans vanished. That raises a tantalizing possibility. What if these dunes aren't just relics of wind, but time capsules from an era when water and air worked together to shape the planet? Parallels don't stop there. On Earth, underwater dunes migrate as currents shift, leaving behind cross-bedded layers that geologists read like tree rings. Mars' dunes have the same layered patterns, preserved in stunning detail because the planet's lack of weather keeps them locked in place. It's like comparing a rushing river to a frozen stream. One is active, the other static, but both tell the same story of movement and change. Yet Mars adds its own twist. Unlike Earth, where underwater dunes are constantly reshaped by tides and storms, Martian dunes might preserve ancient water-altered minerals in their deepest layers. Imagine peeling back those layers like pages in a book, each one revealing a different chapter in Mars' climate history, some written by wind, others by water. That's why missions like the Perseverance rover are so crucial. By studying these dunes up close, we're not just reading the story of Mars' dry present. We're digging into its wet, dynamic past, one grain of sand at a time, and the biggest question remains, if water once interacted with these dunes, could it have left behind more than just minerals? On Earth, submerged dunes teem with microbes that thrive in the interstitial spaces between grains. Mars' dunes may be barren now, but their layers could still hide chemical traces of long-lost brines or even fossilized microbes, locked away in the very sands that once shifted under an alien sea. It's a long shot, but in the search for life beyond Earth, even the longest shots are worth taking. After all, if we've learned anything from studying both planets, it's that the universe loves to repeat its patterns. And sometimes those patterns lead us straight to the answers we've been searching for. Beneath Mars' surface, winding tunnels stretch like hollow veins, collapsed lava tubes that once carried rivers of molten rock across the planet. These eerie passageways, some as wide as subway tunnels, bear a striking resemblance to Earth-submerged caves, those lightless labyrinths carved by water beneath ocean floors or within volcanic islands. On our planet, these hidden chambers are sanctuaries for life in the most hostile conditions. Blind fish, translucent shrimp, and microbes thriving in sulfur-rich waters, cut off from the sun for millennia. So when we find similar structures on Mars, it's impossible not to ask, could these lava tubes have been shelters for alien life, shielding fragile organisms from the planet's punishing radiation and freezing temperatures? The similarities are more than superficial. Earth submarine caves like Mexico's cenotes or the underwater lava tubes off Hawaii are time capsules of extreme habitability. Their walls are often coated in microbial matte slimy, layered communities of bacteria that survive on chemosynthesis, turning rock minerals into energy without a single photon of sunlight. Mars' lava tubes could have offered the same refuge, with ceilings thick enough to block cosmic rays and floors potentially rich in water ice or briny pockets. These tunnels might have created microclimates where life could cling on long after the surface became a desert. Some researchers even speculate that the tube's mineral deposits iron, sulfur, and silica could have fueled subterranean ecosystems, just as they do in Earth's deepest caves. But here's what makes Mars lava tubes even more intriguing. Unlike Earth, where volcanic activity is often paired with abundant water, Mars tubes formed in a drier, colder world. Yet orbital imagery reveals something remarkable. Some tubes appear to have skylights, openings where their ceilings collapsed, exposing icy deposits or frost clinging to the shadows. That's a game changer. If water, even as ice, existed inside these tubes, it could have interacted with the volcanic rock, creating chemical reactions capable of sustaining life. Imagine a scenario where geothermal heat met buried ice, creating damp, warm niches in the darkness far from the deadly surface. The potential for discovery here is staggering. On Earth, caves preserve ancient life like a natural museum. Think of the bacteria found in million-year-old ice or the DNA recovered from subterranean stalactites. Mars lava tubes could be hiding similar treasures, microbial fossils, chemical biosignatures, or even dormant organisms waiting in suspended animation. That's why missions like NASA proposed Moon Diver and concepts for Mars cave rovers are so exciting. By rappelling into these tubes, we could access a pristine record of Mars' hidden past, untouched by dust storms or radiation. Yet the biggest mystery remains: how widespread were these habitable pockets? Some tubes stretch for dozens of kilometers, their walls studded with secondary minerals that hint at ancient water flow. Others show layered sediments, suggesting occasional flooding or seepage. If even a fraction of these tunnels were stable enough to hold liquid water or brines, Mars' subsurface could have been a sprawling network of potential oases, a subterranean world as rich and complex as Earth's deep-sea vents or Antarctic subglacial lakes. So while Mars' surface tells a story of loss, of oceans evaporated and rivers run dry, its underground whispers a different tale. One of resilience, of life hunkering down in the last hospitable corners, and of geological formations so familiar they blur the line between our world and the cosmos. And if we're right about what's hiding in those dark, winding tunnels, the greatest discovery in astrobiology might not be lying in the open, but buried deep beneath our feet, waiting in the echoes of ancient lava flows. Dotting the frozen plains of Mars' Utopia Planitia are strange, dome-shaped mounds, some as tall as a 10-story building, others no bigger than a hillock. These aren't random blisters on the landscape. They're near-perfect matches for Earth's pingos, those icy, water-filled hills that rise like natural igloos in the Arctic. On our planet, pingos form when groundwater, trapped under pressure, freezes and pushes upward, heaving the soil into a swollen dome. Some even burst open like overfilled balloons, spilling their icy guts across the tundra. So when we spot nearly identical formations on Mars, the implications are profound. This wasn't just a world with fleeting water. It had underground reservoirs, freezing and thawing in cycles, creating pockets where life might have found shelter. But Mars doesn't just mimic Earth, it amplifies the mystery. Some of Utopia Planitia's pingo-like mounds stretch for kilometers, their cracked, concentric rings hinting at repeated expansion and contraction, as if the ground itself was breathing. On Earth, that rhythmic swelling is a telltale sign of liquid water shifting beneath the surface, freezing in winter and thawing in summer. If Mars' pingos worked the same way, they'd need a steady supply of groundwater, plus a climate capable of seasonal changes, conditions that would have turned these mounds into miniature oases. Imagine a network of ice-capped domes, their cores laced with briny liquid, shielded from the harsh surface by layers of soil and permafrost. In Earth's Arctic, pingos are hotspots for life, their damp interiors hosting microbes, mosses, and even insects adapted to the freeze-thaw cycle. Could Mars' versions have been just as hospitable? The chemistry adds weight to the idea. Many of these Martian mounds are surrounded by mineral deposits, sulfates, chlorides, and other salts that lower water's freezing point, creating antifreeze-like brines. On Earth, similar brines trickle through Arctic pingos, sustaining ecosystems in what seems like a frozen wasteland. Even in winter, when temperatures plummet, these salty pockets stay liquid, offering refuge to organisms that would otherwise freeze solid. If Mars' pingos harbored similar brines, they could have been biological safe houses, tucked beneath the surface like natural incubators. Yet the most tantalizing clue lies in the cracks. Some of Planitia mounds have fractured summits, just like Earth's pingos when their ice cores melt and collapse. These aren't static relics, they are snapshots of dynamic processes, evidence that Mars' groundwater didn't just exist, it moved, shifted, and reacted to its environment. That's the difference between a planet that was wet once and one that stayed wet long enough for complexity to arise. And here's where the bigger picture comes into focus. Pingos aren't isolated oddities. They're part of a hydrological network fed by underground aquifers and connected to larger climate systems. On Mars, clusters of these mounds suggest something similar, a planet with not just scattered water, but an active, cycling system where moisture migrated between surface and subsurface, ice and liquid. That kind of stability is key for life. It's not about a single wet moment, but a rhythm, a pulse that could sustain organisms over generations. So while these icy mounds might look like simple bumps on a barren plain, they're actually time capsules from a Mars that was far more alive. Not just geologically, but perhaps biologically. And if we're right, the next great discovery in the search for alien life might not come from a dramatic river delta or a deep lake bed, but from these unassuming, frost-covered domes hiding their secrets in plain sight. Stretching across Mars' Meridiani Planum lies a landscape that looks like it was lifted straight from Earth's most arid deserts, vast, flat plains cracked into polygonal patterns, their surfaces glinting with mineral deposits. These are the remnants of ancient playa lakes, the Martian equivalent of Earth's evaporite basins like Death Valley or Bolivia's Salar de Uyuni. On our planet, these bone-dry flats form when temporary lakes evaporate under scorching sun, leaving behind crusts of salt, gypsum, and other minerals that crack and warp as they dry. When NASA Opportunity rover rolled onto Meridiani's plains, it didn't just find rocks. It discovered a chemical graveyard, a place where water had lingered long enough to dissolve, transport, and finally abandon its mineral cargo. The key clue, sulfates, layers upon layers of them, mixed with iron oxides that stained the soil rusty red. On Earth, sulfates like gypsum and epsomite are the calling cards of evaporating water, especially in briny lakes where minerals concentrate as liquid vanishes. In places like Chile's Atacama Desert or Australia's Lake Eyre, these salts pile up into thick, chalky deposits, preserving a record of the water's chemistry long after the lakes disappear. Meridiani's sulfates tell the same story, not of a fleeting puddle, but of persistent, possibly seasonal water bodies that evaporated again and again, each cycle leaving behind another layer of mineral memory. But here's where it gets fascinating. Earth's playas aren't just geological curiosities, they're havens for extremophiles, organisms that thrive in conditions lethal to most life. In the Atacama, bacteria cling to life inside salt crystals, surviving on minuscule traces of moisture. At California's Mono Lake, algae flourish in water 3 times saltier than the ocean. If Mars' playa lakes were similarly brackish, could they have hosted comparable organisms? The chemistry suggests it's possible. Opportunity found not just sulfates, but jarosite and iron sulfate mineral that typically forms in acidic water. On Earth, jarosite-rich environments are often crawling with acid-loving microbes. creatures that turn the minerals sulfur and iron into energy, yet Mars adds a twist to the tale. Unlike Earth's playas, which often refill with seasonal rains, Marineris lakes might have been one-way trips filled by groundwater seeps or flooding, then left to bake dry under a thinning atmosphere. That raises a haunting question: how long did the water last? Some layers show ripples, tiny undulations that suggest wind or gentle waves once stirred these briny shallows. Others contain spherical hematite, blueberries, concretions that form when mineral-rich water percolates through sediment. These features hint at a world where water didn't just vanish overnight, but came and went in cycles, perhaps over thousands of years. The real kicker: on Earth, playa minerals are time capsules. As water evaporates, it traps and preserves organic material, pollen, microbes, even DNA inside crystalline matrices. If Mars' playas did the same, their salt crusts could be hiding chemical fossils, molecular echoes of whatever might have lived there. Future missions could target these deposits, dissolving the salts to hunt for trapped organic compounds, much like scientists now analyze ancient halite crystals from Earth's deserts. So while Marineris' cracked plains might seem lifeless today, they're anything but silent. They're a chemical whisper from a time when Mars was a world of shrinking oases, where water pooled, concentrated, and vanished, leaving behind a puzzle written in salts and sediments. And if we're right about what those minerals are saying, the story might just include a chapter we've never dared to read before. One where life, against all odds, found a way to endure in the last briny puddles of a dying planet. Scattered across Mars' northern plains, you'll find landscapes that look like they've been scooped out by a giant spoon, gentle, bowl-shaped depressions with smooth, scalloped edges. These aren't impact craters or wind-blown pits. They're called scalloped terrains, and they bear an uncanny resemblance to Earth's thermokarst landscapes, those pockmarked regions where permafrost thaws and the ground collapses like a deflating balloon. On our planet, thermokarst forms in places like Siberia and Alaska, where rising temperatures melt buried ice, causing the soil above to slump into watery depressions. So when we see nearly identical features on Mars, it's not just a curious coincidence, it's a smoking gun for subsurface ice, and possibly the volatile chemistry that could have fueled life. The mechanics are strikingly similar. On Earth, thermokarst begins when frozen ground, stable for millennia, suddenly warms. Ice lenses layers of pure ice mixed with soil, melt, leaving behind voids that can't support the weight above. The result, terrain that looks like it's been nibbled away, with scalloped edges and often ponds of meltwater pooling in the hollows. Mars' scalloped terrains mirror this process so precisely that scientists can almost trace the steps: subsurface ice melting, ground collapsing, and dust settling into those signature curves. Some depressions even merge over time, like bubbles in a boiling pot, creating sprawling, interconnected networks of pits. But here's where the Martian twist comes in. Unlike Earth, where thermokarst is driven by climate change or seasonal shifts, Mars scalloping likely happened in fits and starts over millions of years. Orbital images reveal that these features often cluster in regions rich in water ice today, like Utopia Planitia, where NASA Phoenix landers scratched the surface and found icy soil just inches below the dust. That suggests these scallops aren't ancient relics. They might be geologic time stamps, marking periods when Mars wobbled on its axis, tilting just enough to warm its poles and trigger ice melt at mid-latitudes. And then there's the methane connection. On Earth, thawing permafrost is a methane factory. As ice melts, it releases trapped organic matter, which microbes in the soil devour, exhaling methane as a byproduct. In places like Siberia, this process pumps so much gas into the atmosphere that it creates eerie, bubbling lakes. If Mars' scalloped terrains formed the same way, could they have once been methane hotspots too? It's a tantalizing thought. Methane is more than just a greenhouse gas, it's a potential biosignature, a molecule that on Earth is overwhelmingly tied to life. Even if Mars' methane came from geologic processes, like serpentinization where water reacts with certain rocks, its presence would still signal active chemistry in places where ice and heat intersected. The implications are profound. If scalloped terrains are indeed Mars' version of thermokarst, they're not just evidence of ice. They're windows into a dynamic underground, a place where water cycled between solid and gas, where heat and chemistry might have created temporary oases. Picture this: pockets of liquid water pooling beneath collapsed ground, shielded from the harsh surface, while methane seeped through the soil like a slow breath. On Earth, such environments teem with methanogens, microbes that thrive in oxygen-free zones, turning hydrogen and carbon dioxide into methane. Could Mars' depressions have hosted similar organisms, clinging to the edges of thawing ice? Yet mysteries linger. Without active plate tectonics or volcanic heat, how did Mars' subsurface ice melt so uniformly? Some researchers point to asteroid impacts, which could have delivered short-lived bursts of heat, triggering regional thaw. Others suggest atmospheric changes, brief spikes in temperature or pressure that allowed ice to sublimate directly into vapor, undermining the ground. Whatever the cause, these scalloped terrains are more than just scars on a frozen desert. They're clues to a time when Mars wasn't just cold and dry, but a world of hidden thaw and flow, where the very ground breathed methane and water lurked just out of sight. So the next time you see those smooth, scooped hollows on a Martian map, remember, they're not just pits, they're echoes of a planet that refused to freeze quietly, a place where ice, heat, and chemistry might have conspired to create something extraordinary. And if we're right about what happened there, the story of life in the universe could be hiding in the unlikeliest of places, the soft, scalloped curves of a long dormant landscape. Now, let's talk about one of Mars' most jaw-dropping features, Valles, a sprawling network of channels so vast they make Earth's largest rivers look like trickles in the sand. These aren't gentle waterways carved by patient erosion. They're the scars of catastrophe, the aftermath of floods so powerful they could have ripped through entire continents. And here's the eerie part. They're nearly identical to the channeled scablands of Washington state, where Earth's own megafloods once tore across the landscape with unimaginable force. The parallels are impossible to ignore. On Earth, the scablands were carved by glacial outburst floods, torrents unleashed when ancient ice dams ruptured, sending walls of water crashing across the land at speeds approaching 100 kilometers per hour. The result, a ravaged terrain of dry waterfalls, colossal potholes, and braided channels etched into bedrock. Valles mirrors this devastation on an even grander scale. Some of its channels stretch over 3,000 kilometers long and plunge 4 kilometers deep, with teardrop-shaped islands and streamlined mesas that point to flows so violent they could have swallowed entire cities whole. But the real mystery isn't just the scale, it's the source. On Earth, megafloods like the Missoula floods had a clear origin, melting ice sheets. Mars, though, lacks glaciers of that magnitude today. So where did all that water come from? Some scientists point to underground aquifers, pressurized reservoirs that burst through the crust like a popped lid on a shaken soda bottle. Others suggest volcanic heat melting buried ice caps, triggering tsunamis of slurry, part water, part mud, part rock, that scoured the land as they raced downhill. Either way, the numbers are staggering. estimates suggest Valles floods carried 10 times the flow of the Amazon River, with enough water to cover the entire planet in a shallow ocean if spread evenly. And that's where the puzzle deepens. Floods that immense don't just vanish without a trace. On Earth, the Scablan's floodwaters drained into the Pacific, leaving behind a reshaped continent. But Mars has no global ocean to swallow its deluge. So where did the water go? Some might have evaporated into the thin atmosphere, escaping into space over millennia. Some could have frozen underground, forming the icy layers we detect today beneath the dust. But here's the haunting possibility. What if some of it lingered? Imagine vast lakes forming in the flood's wake, pooling in low-lying basins like Hellas or Argyre. These wouldn't have been temporary puddles. They could have lasted for centuries, even millennia, before finally drying up. And if that's true, they might have been the last hospitable refuges for any life clinging to survival. On Earth, flood-scoured landscapes like the Scablan's are ecological reset buttons, but they're also rebirths. Newly carved channels become wetlands, and temporary lakes teem with nutrients. Could Mars' outflow channels have offered the same fleeting promise? The answer might lie in the minerals. Valles channels are lined with clays and sulfates, telltale signs of water-altered rock. Some patches even show hydrated minerals that suggest water didn't just rush through, it soaked in, lingering long enough to chemically transform the landscape. That's the difference between a flash flood and a sustained deluge, between a single disaster and an era of change. Yet the most profound question remains unanswered. If Mars had floods this colossal, what triggered them? On Earth, climate shifts and glacial dynamics are the culprits, but Mars floods seem tied to something more sporadic. Perhaps asteroid impacts cracking the crust, or volcanic eruptions melting ice fields in sudden, apocalyptic bursts. Each scenario paints a different picture of Mars' past, one where the planet didn't just dry up quietly, but convulsed in fits of violence, its water unleashed in catastrophic spasms before finally slipping away. So when you see those winding, scarred channels on a map of Mars, remember, you're not just looking at dry riverbeds, you're seeing the echoes of a planet in upheaval, a world that didn't lose its water gently, but in a series of roaring, landscape-shattering goodbyes. And somewhere in those flood-carved valleys, there might just be clues to how long those farewells lasted and what they left behind. Buried in the Martian soil like tiny iron marbles, the so-called blueberries discovered by NASA's Opportunity rover aren't just geological oddities, they're miniature time capsules, each one holding secrets about Mars' watery past. These spherules, no larger than peppercorns, are made of hematite, an iron oxide that on Earth often forms in the presence of liquid water. But what makes them truly fascinating is their uncanny resemblance to iron concretions found on our own ocean floors, those lumpy, potato-shaped nodules that grow layer by layer as mineral-rich water percolates through sediment. It's as if Mars took a page from Earth's playbook, using the same chemical processes to craft these tiny orbs, but on a world where water vanished billions of years ago. The parallels between Mars' blueberries and Earth's marine concretions are too precise to dismiss. On our planet, these nodules form in places like the Baltic Sea or the Pacific's abyssal plains, where dissolved iron in groundwater reacts with oxygen or microbes, slowly precipitating into compact spheres. The process is achingly slow. Some concretions take millions of years to grow, their layers recording fluctuations in water chemistry like tree rings. Mars' hematite spherules likely formed the same way, their concentric layers hinting at a time when groundwater seeped through the planet's rusty soil, depositing iron oxide grain by grain. The key difference: on Earth, these nodules often form in active marine environments, bathed in oxygen and organic matter. On Mars, they're fossils of a lost hydrological system, frozen in time when the water disappeared. Yet the real magic lies in what these spherules might preserve. On Earth, iron concretions are notorious for trapping and protecting organic material. In places like Utah's Jurassic Age Navajo sandstone, they've been found enclosing fossilized bacteria, even delicate strands of ancient DNA. The iron acts like a natural embalming fluid, preventing decay by sealing off microbes from oxygen and predators. If Mars blueberries formed under similar conditions, they could be hiding microscopic treasure, chemical residues of long-dead organisms, or at least the molecular building blocks they left behind. It's no wonder scientists refer to them as Mars lucky charms, a tiny, unassuming objects that might just hold the key to the planet's biggest mystery. But here's the twist: not all blueberries are created equal. Some are dense and solid, while others are hollow or fractured, suggesting variations in how they formed. On Earth, this diversity would point to differences in water chemistry, perhaps shifts in acidity, salinity, or the presence of microbes. On Mars, it could mean these spherules record a changing environment, one where water grew scarcer or more acidic over time. Imagine a scenario where early Mars had neutral, life-friendly groundwater, but as the planet dried up, the remaining pockets became briny and harsh, altering how the hematite precipitated. The blueberry structure would carry that story, their layers encoding the planet's slow descent into aridity. That's why rovers like Opportunity and Perseverance spend so much time studying these tiny spheres. Each one is a snapshot, a frozen moment in Mars' geological history. By analyzing their composition, texture, and distribution, scientists can reconstruct the conditions that shaped them. Was the water warm or cold, flowing or stagnant? Full of chemical energy or barren? The answers could rewrite our understanding of Mars' habitability, proving it wasn't just wet, but hospitable for long enough to let life take root. And the implications stretch beyond Mars. If two planets separated by millions of kilometers, both crafted nearly identical iron spherules through watery chemistry, what does that say about the universe's playbook for shaping worlds? Perhaps these tiny orbs are more than just curiosities, they're universal signatures, a way for planets to whisper across the cosmos that water was here, that conditions were right, and that the story might not have ended when the oceans dried up. So the next time you see a photo of Martian soil dotted with those innocuous blueberries, remember, they're not just rocks, they're messages written in iron and time, waiting for us to decode their rust-colored secrets. Across Mars' sun-baked plains, a strange phenomenon unfolds: dark, twisting scribbles that snake across the surface like the work of a cosmic pen. These are dust devil tracks, the ephemeral graffiti left behind by whirlwinds of Martian air, spinning dust into towering columns that can reach heights of 8 kilometers. But here's the twist: while they might look like random scribbles at first glance, these trails bear a startling resemblance to the ripple marks etched into Earth's ocean floors by deep sea currents. On our planet, underwater flows sculpt sediment into delicate ridges and furrows, creating patterns that record the direction and strength of unseen forces. Mars dust devil tracks do the same, only instead of water, they're shaped by the whisper-thin atmosphere, dancing across the surface like ghosts of long-lost currents. The physics behind these patterns is eerily similar. On Earth, ocean currents drag along the seafloor, pushing loose sediment into rhythmic waves that can stretch for miles. The finer the grains, the more delicate the ripples, a language of motion written in sand and silt. Mars dust devils follow the same rules. As these whirlwinds skim the surface, they scoop up fine, dark dust, exposing brighter substrate beneath. The result, striking serpentine trails that reveal the path of the vortex, its speed, and even the texture of the soil it's traversing. It's fluid dynamics in action. Just swap water for air and seabed for desert. But the real intrigue lies in what these dust devils might be carrying. Recent studies suggest they're not just moving dust. They could be redistributing water-altered minerals like sulfates and clays, scouring them from one location and depositing them elsewhere. On Earth, underwater currents do something similar, transporting nutrient-rich sediments that feed entire ecosystems on the seafloor. If Mars dust devils are shuffling hydrated minerals across the surface, they might be creating accidental oases, patches where water-friendly chemistry briefly concentrates, offering potential havens for any hardy microbes that could still cling to existence. The scale of this process is staggering. Some Martian dust devil tracks stretch for hundreds of kilometers, weaving around craters and over hills like colossal, meandering rivers. Orbital images even show tracks crossing each other in intricate braids, a record of seasonal wind patterns written in dust. Compare that to Earth's abyssal plains, where deep currents leave behind overlapping ripple marks that tell oceanographers the story of ancient tides and storms. Both are planetary diaries, one written by water, the other by wind. Yet Mars adds a layer of mystery. Unlike Earth, where ocean currents are driven by tides, temperature gradients, and the planet's rotation, Mars dust devils seem to spring from a simpler recipe: sunlight heating the surface, creating convection cells that twist into spinning vortices. But occasionally, they defy expectations. Some whirlwinds leave behind bizarre, zigzagging tracks, suggesting encounters with obstacles or shifts in wind shear. Others seem to vanish abruptly, their trails ending as if the dust devils simply dissolved into thin air, a reminder that even on a planet we're mapping in high definition, some phenomena remain tantalizingly unpredictable. What's most compelling, though, is the way these tracks bridge Mars' past and present. The minerals they redistribute might have formed billions of years ago, when liquid water still pooled on the surface. Now they're being shuffled by winds, creating a dynamic interplay between ancient chemistry and modern geology. It's as if the planet is constantly remixing its own history, scattering clues where we least expect them. So the next time you see those eerie, looping trails on a Martian landscape, remember, you're not just looking at wind patterns, you're witnessing a cosmic echo, a reminder that even in the absence of oceans, the same fundamental forces shape worlds, whether with water or wind, in the deep sea or the deep desert. And somewhere in those twisting tracks, there might just be a whisper of the most elusive secret of all, a sign that Mars, in its own quiet way, is still alive. Jezero Crater isn't just another dent on Mars' battered surface, it's a time machine. This ancient basin, now home to NASA's Perseverance rover, was once a sprawling lake, its waters fed by a river that carved a delta so pristine it could have been lifted straight from Earth's geologic record. And that's no accident. Jezero's story mirrors our own planet's impact basins, like Canada's Clearwater Lakes or Germany's Nördlinger Rise, where asteroid strikes created hollows that later filled with water, becoming crucibles for life. The difference, while Earth's lakes have been reshaped by millennia of rain and tectonics, Jezero's remains frozen in time, a snapshot of a moment when Mars was blue, not red. What makes this crater so special is its delta, a fan-shaped deposit of sediment so textbook perfect it could grace a geology lecture. On Earth, deltas are nature's filing cabinets. As rivers slow and spill into lakes, they dump their cargo of sand, silt, and organic debris, layer by layer, creating a natural archive of everything that once flowed downstream. The Mississippi Delta preserves pollen from ancient forests. The Nile holds fossils of long-extinct fish. Jezero's delta, scientists suspect, could be hiding similar treasures, perhaps even the holy grail of Martian exploration, fossilized microbes. The chemistry here is tantalizing. Orbital scans reveal carbonates lining Jazero's shores, minerals that on Earth often form in shallow, sunlit waters ideal for microbial mats. The delta itself is rich in clays, which not only trap organic material but protect it from radiation like a natural vault. And then there's the crater's history. Jezero didn't just hold water, it held it long enough for sediments to pile up into distinct layers, suggesting a stable, enduring environment. That's the sweet spot for life. On Earth, impact-formed lakes are biodiversity hotspots precisely because they offer consistency, a place where organisms can settle, adapt, and leave behind evidence of their existence. Yet Mars throws us a curveball. Unlike Earth's lakes, which are often refreshed by rainfall or underground springs, Jazero's waters likely came and went in fits and starts. Some layers in the delta hint at violent floods, while others speak of calm, persistent flow. This isn't just a story of a lake, it's a record of climate swings, of a planet teetering between wet and dry. And that's what makes Perseverance's mission so revolutionary. By drilling into these layers, the rover isn't just reading rocks, it's decoding Mars' mood swings, searching for the intervals when conditions were just right for life to grab hold. The parallels to Earth's fossil beds are impossible to ignore. In places like Wyoming's Green River Formation or Mongolia's ancient Gobi lakes, exquisitely preserved fish, insects, and even feathers are found in sediment laid down in still, oxygen-poor waters, conditions that slow decay and leave fossils pristine. Jazero's delta, with its fine-grained clays and quiet depositional environment, could be Mars' version of these natural museums. Even if life there was microscopic, the right minerals might have captured its imprint, locking away cellular shapes or chemical signatures in stone. But the real magic lies in Jazero's dual nature. As an impact crater, it's a wound from Mars' violent past. As a lakebed, it's a sanctuary where water soothed that violence, turning chaos into a cradle. That duality is key. On Earth, impact basins like Sudbury in Canada became nurseries for early life precisely because they mixed heat, water, and minerals, a recipe for chemistry to turn into biology. If Jezero followed the same script, the fossils Perseverance seeks might not just be remnants. They could be proof that even in the aftermath of cosmic violence, the universe finds a way to whisper the possibility of life. So while Jazero's waters are long gone, their legacy isn't. Every layer Perseverance samples is a page in a story we're only beginning to read, one where Mars wasn't a lifeless rock, but a world of shimmering lakes, their surfaces reflecting not just sunlight, but the faint, flickering hope that we're not alone in the cosmos. And if we're lucky, the next chapter of that story might be written in the faintest of traces, a fossil too small to see, but vast enough to change everything. Stretching across Mars' southern highlands, vast patches of chloride salts gleam like ghostly stains, pale, cracked remnants of what might have been the red planet's last standing bodies of water. These deposits, spotted by orbiters like NASA Mars Reconnaissance Orbiter, aren't random sprinkles of crystals. They're concentrated in basins and low-lying plains, forming intricate patterns that mirror Earth's own salt flats, like the Bonneville Salt Flats in Utah or the otherworldly expanse of Chile's Atacama Desert. But the most striking parallel, the Dead Sea. Just as this hypersaline lake leaves behind thick crusts of salt as it evaporates, Mars' chloride patches seem to mark the final gasp of ancient lakes or even shallow seas, their waters retreating under a thinning atmosphere until only briny residue remained. The science behind these salts is a detective story written in chemistry. On Earth, chloride deposits form when water rich in dissolved minerals. Think of the Great Salt Lake or the evaporating playas of Death Valley, dries up, leaving behind concentrated layers of salt. The process isn't gentle. As water vanishes, it abandons everything it once carried, creating stark, mineral-rich landscapes where little can survive. Mars salts tell the same tale, but with a twist. Unlike Earth's dynamic environments, where new sediments often bury old salt layers, Mars deposits sit exposed, preserved in eerie perfection for billions of years. They're not just relics of water, they're tombstones, marking exactly where and how the planet's moisture disappeared. What's fascinating is the scale. Some of Mars' salt deposits span hundreds of square kilometers, suggesting bodies of water far larger than individual lakes, perhaps even regional seas. The distribution is telling, too. Many clusters sit at the lowest elevations, just as Earth's salt pans gather in basins where water pools before evaporating. This isn't accidental. It's physics in action, a universal rule that water follows gravity until it's wrung dry. And just like Earth's Dead Sea, which shrinks a little more each year due to human diversion, Mars salts might record a climate crisis of cosmic proportions, a planet losing its water not to irrigation, but to a collapsing atmosphere. But here's where the mystery deepens. On Earth, salt flats aren't just barren wastelands. They're extreme habitats, home to hardy organisms like halophiles, microbes that thrive in salt, using it to stabilize their cells against desiccation. In places like Chile's Salar de Atacama, these creatures tint the salt pink with their pigments, a vivid sign of life clinging to the harshest conditions. If Mars chloride deposits formed in similar environments, could they have hosted comparable life? It's a tantalizing thought. Salt doesn't just preserve landscapes, it's a natural conservator, trapping and protecting organic material for millennia. On Earth, ancient salt crystals have been cracked open to reveal trapped microbes dating back hundreds of millions of years. Mars salts could be hiding similar surprises, their crystalline structures acting as tiny vaults for whatever might have lived in those long-vanished brines. Yet Mars throws us a curveball. Unlike Earth, where salt deposits often cycle through wet and dry phases, Mars salts seem to have formed during the planet's final act of drying out. Some scientists believe they mark the transition from a world with persistent water to the arid desert we see today. That makes them chronological bookmarks, pinning down the moment Mars crossed the threshold from habitable to hostile. The salts themselves hold clues. Variations in their chemistry could reveal whether evaporation was slow and steady or sudden and catastrophic, whether the water was mildly brackish or as harsh as battery acid. The implications ripple outward. If these deposits are the fingerprints of vanished oceans, they could help solve one of Mars' biggest puzzles. Where did all the water go? Some might have escaped to space, but some could still lurk underground, locked in briny aquifers or ice. Future missions targeting these salt zones might drill into them, searching not just for traces of ancient life, but for liquid remnants of those lost seas. Imagine discovering that Mars' great oceans didn't fully vanish, they just retreated, hiding in the very salts they left behind. So the next time you see those pale, cracked patches in orbital images, remember, they're not just stains. They're the last echoes of a planet's thirst, a cosmic lesson in what happens when water runs dry. And if we're lucky, they might just hold the key to understanding not just Mars' past, but the fragile balance that keeps any world alive. Tucked along the flanks of Martian valleys and craters, strange, tongue-shaped formations creep across the landscape, lobate debris aprons, the frozen ghosts of ancient glaciers. These sprawling, hummocky deposits look eerily like Earth's glacial moraines, those rugged piles of rock and sediment bulldozed by advancing ice sheets during our planet's ice ages. The resemblance isn't superficial. Just as Earth's glaciers sculpt valleys and grind nutrients into fertile soil, Mars' lobate aprons hint at a time when ice, not dust, ruled the red planet's highlands. But here's the electrifying question. If Mars' glaciers were anything like ours, could they have done more than just carve rock? Could they have created hidden oases, pulverizing minerals into life-friendly chemistry beneath their icy weight? The mechanics are strikingly familiar. On Earth, glaciers act like planetary conveyor belts, scraping bedrock and churning it into fine powder as they inch forward. This glacial flour isn't just debris. It's a cocktail of crushed minerals from phosphorus to iron, all ground into forms that water can dissolve and life can use. In places like Alaska's Copper River Valley, this nutrient-rich slurry feeds entire ecosystems, fueling phytoplankton blooms that ripple up the food chain. Mars' lobate aprons, with their telltale ridges and grooves, suggest similar grinding action. Orbital radar has even detected ice-rich layers beneath their surfaces, as if the glaciers never fully vanished. They just retreated underground, leaving behind frozen rubble as a clue. But the real intrigue lies in what those glaciers might have unlocked. On Earth, ice sheets don't just move rock, they create microenvironments. Subglacial lakes like Antarctica's Lake Willen's teem with microbes that thrive in the dark, fed by minerals pulverized by the ice above. If Mars' glaciers were thick enough to generate similar pressure and friction, their bases could have hosted thin films of liquid water, even in freezing temperatures. Picture this, a slow-flowing Martian glacier, its underside warmed by geothermal heat or the sheer force of movement, grinding iron-rich basalt into reactive powder. Mix that with trapped meltwater, and you've got a chemical reactor, one that could have churned out hydrogen, sulfates, or other energy sources for microbial life. The evidence is mounting. Some lobate aprons are surrounded by lineated valley fill, grooved terrain that looks like it was smeared by ice flow. Others sit at the mouths of valleys that funnel into basins, perfect settings for glacial meltwater to pool. Even more compelling, many aprons are studded with boulders that match the composition of nearby cliffs, as if the ice plucked them straight from the bedrock, a classic glacial signature. It's as if Mars left us a textbook on Ice Age geology, only the chapters are written in landforms instead of words. Yet the biggest mystery isn't whether Mars had glaciers, it's how they behaved. On Earth, glaciers advance and retreat with climate cycles, driven by wobbles in our planet's orbit. Mars has its own orbital quirks, but with a thinner atmosphere and no moon to stabilize its tilt, its ice ages would have been wilder, more extreme. Some scientists believe the lobate aprons might be remnants of cold-based glaciers, which slide less than Earth's but still deform internally, creeping like molasses over millennia. Others argue they're debris-covered glaciers, their ice shielded from sublimation by a protective blanket of rubble. Either way, they're not static relics. Recent studies suggest some might still be slowly flowing today, locked in a slow-motion dance between freeze and thaw, and that's where the search for life gets thrilling. On Earth, subglacial environments are time capsules, preserving ancient microbes in ice for millions of years. If Mars' glaciers once harbored similar niches, their remnants could be treasure troves. Future missions might drill into these aprons, hunting not just for ice but for chemical traces of past activity, perhaps even cryopreserved cells, frozen in place when the ice last retreated. It's a long shot, but consider this. Earth's glaciers have been caught red-handed carrying microbes across continents. If Mars' ice did the same, its moraines might be more than just rubble piles. They could be icy arcs, ferrying life's last survivors to their final refuge. So while these hummocky aprons might look like barren wastelands, they're anything but. They're frozen almanacs of a time when Mars wasn't just cold but dynamic, a world where ice sculpted valleys, ground nutrients, and maybe, just maybe, offered life one last place to hide. And if we're right about what's buried beneath them, the discovery wouldn't just rewrite Martian history. It would prove that even in the deepest freeze, the universe finds a way to keep the embers of life flickering. Stretching across Mars like a jagged scar, the Cerberus fossae fissures are more than just cracks in the planet's crust. They're a window into a time when the red planet may have pulsed with geological activity eerily similar to Earth's mid-ocean ridges. These yawning chasms, some over 1,000 kilometers long and several kilometers wide, aren't random fractures. They're tectonic masterpieces, forged by the same forces that rip apart Earth's seafloor, creating undersea rifts where life thrives against all odds. The parallels are uncanny. Just as Earth's mid-ocean ridges spew mineral-rich fluids and heat from the planet's depths, Cerberus fossae shows signs of ancient volcanic eruptions and even possible groundwater seepage, as if Mars once had its own version of hydrothermal vents, those deep-sea oases where entire ecosystems flourish in total darkness. What makes these fissures so compelling is their sheer dynamism. On Earth, mid-ocean ridges are planetary sutures, places where tectonic plates diverge and magma wells up to create new crust. The process isn't just geologic, it's biological. Superheated water loaded with sulfur and metals gushes from these rifts, feeding bacteria that form the base of a food chain stretching to giant tube worms and ghostly octopuses. Cerberus fossae may lack oceans, but orbital data reveals telltale minerals like olivine and serpentine along its walls, clues that hot water once interacted with rock here. That's the smoking gun. Where there's heat, water, and chemistry, there's potential for life, or at least the conditions that could have nurtured it billions of years ago. The scale of these fissures hints at something even more profound. Unlike Earth's ridges, which are constantly recycled by plate tectonics, Mars' cracks are frozen in time, preserving a record of the planet's internal struggles. Some sections of Cerberus fossae are flanked by smooth, flat plains, evidence of ancient lava, flows that may have oozed from the fractures like blood from a wound. Other areas show collapsed pits and chains of depressions, suggesting subterranean voids where groundwater might have pooled before draining away. It's as if we're looking at a snapshot of Mars' last gasp, the moment when its core cooled, its tectonics stalled, and its water retreated underground. Yet the most tantalizing possibility lies in what might still lurk beneath. On Earth, life doesn't just cluster around active vents, it infiltrates the rocky crust itself, with microbes thriving in tiny fractures miles below the seafloor. These deep biosphere organisms live on chemical energy, indifferent to sunlight or surface conditions. If Mars fissures once hosted similar fluids, their deep, sheltered fractures could have been ideal hideouts for microbial life, shielded from the planet's worsening climate. Even today, residual heat from Mars' interior might keep brines liquid in isolated pockets, creating modern-day refuges where life, if it ever existed, could cling on. The comparison to Earth's rifts goes beyond biology. Cerberus fossae's geometry, its straight, parallel walls and steep cliffs, mirrors the structure of Earth's mid-ocean ridges so precisely that it's hard to dismiss the connection. Both are products of crustal stretching, places where the planet's skin split under tension. The difference is timing. Earth's ridges are alive, constantly birthing new seafloor. Mars' fissures are a fossilized echo of that process, a reminder that tectonic forces once shaped this world too. That duality raises a haunting question. If Mars had plate tectonics, even briefly, could it have sustained the kind of long-term habitability that nurtures complex life? On Earth, tectonics recycle nutrients, regulate climate, and maintain the magnetic field that deflects deadly radiation. Without those cycles, Mars was doomed to dry out. But in Cerberus Fossey's heyday perhaps 2 or 3 billion years ago, the planet might have had just enough geologic vigor to keep water circulating, minerals mixing, and energy flowing. It's a fragile window, but for life, even a fleeting chance is better than none. So while these fissures may seem like barren gashes today, they're anything but. They're time capsules from an era when Mars wasn't just geologically active. It was a world of hidden heat, flowing fluids, and perhaps, just perhaps, the faintest whisper of life. And if we're right about what once bubbled up from those cracks, the story of life in the universe might not be confined to ocean worlds. It could be written in the scars of planets that tried, but couldn't quite hold on to their magic. Gliding down Martian slopes like shadowy fingers, the mysterious dark streaks known as recurring slope lineae have sparked one of the most heated debates in planetary science. These fleeting markings, which appear seasonally on sun-warmed inclines, darken and fade with the rhythm of Mars' orbit, almost as if something liquid is briefly surfacing before vanishing into the thin air. The most tantalizing theory: these streaks could be seeps of briny water, oozing from underground reservoirs much like Earth's submarine springs, where mineral-rich fluids percolate through cracks in the ocean floor to feed lush ecosystems in the abyss. If true, this wouldn't just be a relic of Mars' wet past, it'd be proof that water still moves on the red planet today. The parallels to Earth's hidden seeps are striking. Along mid-ocean ridges and continental shelves, hydrothermal vents gush superheated fluids loaded with dissolved salts, while colder seeps slowly leak methane and brines through sediment. Both create dark, sinuous stains on the seafloor, visible in sonar scans as branching networks that shift over time. Mars RSL mirrors this behavior with uncanny precision. Spectroscopic data from orbit reveals hydrated salts, magnesium perchlorate, sodium chlorate along the streaks, compounds that lower water's freezing point enough to keep it liquid in Mars' sub-zero chill. These aren't random chemical stains. They're the exact fingerprints you'd expect from briny water trickling to the surface, depositing salts as it evaporates in the arid Martian atmosphere. But here's where the mystery twists. Unlike Earth seeps, which are powered by tidal forces or geothermal heat, Mars' potential briny flows operate in near silence. Some scientists argue dry landslides or shifting dust could mimic the streaks without any water at all, yet the seasonal timing defies easy dismissal. RSL predominantly appear during Mars' warmer months, vanishing when temperatures drop, a cycle that mirrors how Antarctic brine channels darken in summer as ice melts. Even more compelling, the streaks cluster on steep, sun-facing slopes, exactly where solar heating would maximize any subsurface thaw. It's as if Mars is whispering where to look for its hidden wet spots. The implications ripple far beyond geology. On Earth, submarine seeps are biodiversity hotspots, their chemical soups fueling bacteria that support tube worms, clams, and eyeless shrimp. If RSL are truly briny seeps, they could be modern-day oases, however fleeting. The salts-involved perchlorates are toxic to most Earth life, but extremophiles like some desert microbes not only tolerate them, they use them as energy sources. Picture a scenario where Martian microbes, if they exist, lie dormant in icy fractures, awakening briefly when summer warmth liquefies their briny refuge, then retreating as winter freezes them solid again. It's a haunting echo of life in Earth's driest deserts, where organisms wait years for a drop of rain. Yet the debate rages on. recent experiments show that dry, granular flows of sand and dust can replicate RSL-like streaks in Mars-like conditions. Other studies point to carbon dioxide frost sublimation as a possible trigger. The truth might lie somewhere in between, perhaps a mix of trace moisture lubricating dust slides, creating hybrid features that aren't purely wet or dry. That ambiguity is what makes RSL so fascinating. They're a cosmic Rorschach test, revealing just how hard it is to interpret another world's processes through an earthly lens. What's undeniable is the urgency to solve this puzzle. If these streaks do harbor liquid water, however brackish, they'd top the list for astrobiological exploration. NASA planetary protection protocols already treat RSL sites as special regions, restricting rover visits to avoid contamination. Future missions might deploy drills or heated probes to sniff for vapor emissions, or even attempt to catch a streak in the act of forming. Imagine the day we finally witness in real time water, or something like it, still shaping the surface of Mars. Until then, these shadowy streaks remain one of the solar system's most tantalizing maybes. They challenge our definitions of habitability, our assumptions about where life can cling, and our understanding of how water behaves on worlds unlike our own. And whether they're damp seeps or dusty illusions, they prove one thing beyond doubt: Mars still has secrets left to spill. Rising from Mars' arid plains like the fossilized spines of ancient beasts, Yardangs are nature's testament to the relentless power of wind. These razor-backed ridges, some stretching for hundreds of kilometers, are the red planet's answer to Earth's most dramatic seabed formations, sculpted not by water, but by millennia of abrasive dust storms scouring the landscape grain by grain. What makes these wind-carved sentinels so fascinating isn't just their otherworldly appearance, it's how closely they resemble underwater features on our own planet, where currents rather than gusts perform the same meticulous work of planetary artistry. Take a closer look at these Martian Yardangs, and you'll spot grooves and flutes running parallel along their length, the unmistakable signature of fluid flow. On Earth, identical patterns appear on the ocean floor, where deep sea currents have streamlined mud banks into elongated ridges, like the giant sediment waves off the coast of Brazil. The physics at play are universal. Whether it's water moving at 15 centimeters per second or Martian winds blasting at hurricane speeds, any fluid, no matter its composition, will sort and shape loose material into these aerodynamic forms given enough time. It's a cosmic lesson in erosion, written in two different languages, one aquatic, one atmospheric. The scale of Mars' Yardang fields dwarfs anything on Earth. In places like the Medusae Fossae Formation, these wind-sculpted ridges march across the horizon like a frozen tsunami wave, some towering over 200 meters tall. Compare that to Earth's largest underwater Yardangs, found in places like the Bering Sea's canyon systems, where they might reach 20 meters at most. This disparity speaks volumes about Mars' environmental extremes. Its thinner atmosphere requires faster winds to move particles, but with no vegetation or moisture to stabilize the surface, erosion runs unchecked for eons. The result, landscapes that look like they've been sandblasted for billions of years, because essentially they have. Yet the most compelling parallel lies in the details. Both Martian Yardangs and their aquatic earthly counterparts often form in sedimentary rock, soft, layered materials that record climate history like geological tape recorders. On Earth, submarine Yardangs in places like the English Channel preserve evidence of ancient current directions, helping oceanographers reconstruct prehistoric sea circulation. Mars Yardangs serve a similar purpose, Their orientation maps the planet's dominant wind patterns, revealing how atmospheric circulation has shifted over time. Some fields even show multiple Yardang directions superimposed, suggesting dramatic changes in Mars' climate regime, perhaps as its atmosphere thinned or its axial tilt wobbled. What truly sparks the imagination, though, is how these formations blur the line between wind and water. In Egypt's Qattara Depression, Yardangs carved by desert winds stand shoulder to shoulder with identical structures formed by ancient floods, their forms indistinguishable except to trained geologists. Mars presents the same enigma without liquid water visibly active today. We assume its Yardangs are purely Aeolian. But what if some formed underwater in Mars' distant past, only to be modified later by wind? The possibility isn't far-fetched. Several Yardang fields cluster near what were likely ancient shorelines, their bases sometimes layered with water-deposited minerals. This duality makes them double agents in Mars' climate history, potentially recording both aquatic and atmospheric chapters in their striated flanks. The implications stretch beyond geology. On Earth, submarine Yardangs often become biodiversity hotspots. Their ridges and troughs create microhabitats where currents concentrate nutrients, attracting everything from plankton to gray whales. While Mars' wind-scoured ridges seem lifeless today, their layered sediments might preserve chemical traces of the planet's wetter eras. Future missions could target these formations not just to read wind patterns, but to hunt for evaporite minerals or even organic compounds trapped between their strata. After all, if Earth's underwater Yardangs can be time capsules, why not Mars' aerial ones? Ultimately, these parallel landscapes remind us that the universe works with a limited toolkit. Whether shaped by the persistent whisper of ocean currents or the scream of Martian dust storms, Yardangs tell the same fundamental story, that given enough time, even the softest touch of moving fluid can carve a world into something extraordinary. And on Mars, where wind is the last great sculptor still at work, they stand as monuments to patience, a reminder that change doesn't always come in cataclysms, but sometimes in the accumulated breath of countless storms. Towering over Mars' Elysium Planitia, the solitary peak of Elysium Mons rises like a sentinel, a volcanic giant whose slopes tell a story that blurs the line between worlds. At first glance, this massive shield volcano resembles Hawaii's Mauna Loa or the Azores' Pico Island, formations born from fiery eruptions beneath Earth's oceans. But here's the twist. If Mars once had vast northern oceans as scientists suspect, Elysium Mons wouldn't have been just a mountain. It would have been an island, its flanks lapped by waves, its summit piercing the atmosphere like a beacon. This isn't just geology, it's planetary poetry, a hint that Mars' volcanic past might have created isolated habitats as rich and unique as Earth's most remote island ecosystems. The similarities between Elysium Mons and Earth seamounts run deep. Both share that distinctive low-angle profile, the hallmark of shield volcanoes built by countless fluid lava flows piling up over millennia. On Earth, underwater volcanoes like Loihai or the Emperor seamounts grow slowly as magma oozes through the seafloor, their sides sculpted by water's cooling touch. Elysium Mons' gently sloping flanks suggest a similar origin, perhaps even undersea eruptions if Mars' ocean theories hold. Orbital scans reveal something even more compelling. What appear to be ancient lava deltas near its base, terraces that on Earth form when molten rock meets water and shatters into glassy fragments. These aren't just random features. They're potential shorelines, frozen snapshots of a time when lava and liquid might have coexisted on Mars' surface. Imagine standing on Elysium Mons slopes 3 billion years ago. The air would have been thicker, the sky hazy with volcanic vapors, Below, an ocean stretches to the horizon, its waves etching beaches into fresh black sand. This scenario isn't science fiction. On Earth, volcanic islands are crucibles of evolution, their isolation giving rise to species found nowhere else. Think of the Galapagos marine iguanas or Hawaii's honeycreepers. If Mars had similar islands, their coasts could have been hotspots for chemical complexity, where volcanic minerals mixed with seawater to create nutrient-rich soups. Hydrothermal vents around the base might have bubbled with warmth, mimicking Earth's lost city hydrothermal field, where alkaline fluids fuel microbial communities without sunlight. The ingredients were all there: energy from volcanism, water as a solvent, and minerals to build organic molecules. But Mars adds layers of mystery. Unlike Earth's constantly recycled seafloor, Elysium, Mons' underwater past, if it existed, is preserved in amber. The mountain's western flanks show strange, knobby textures that resemble pillow lavas, the bulbous formations created when lava erupts underwater and forms a glassy skin. Nearby, channels snake down the slopes, possibly carved by steam explosions as lava met water, or even by tsunamis triggered by collapsing eruption columns. These details matter because they suggest dynamic interactions between fire and water, the kind of violent chemistry that on Earth creates niches for extremophiles. In Iceland's shallow marine vents, for example, bacteria thrive in boiling, mineral-laden water, their proteins adapted to withstand conditions that would cook most life. If Mars had similar environments, even briefly, they could have been incubators for simple organisms. The most tantalizing clues lie in the minerals. Elysium Mons' surroundings are strewn with olivine and pyroxene, iron-rich crystals that on Earth react eagerly with water to produce hydrogen, a potential energy source for microbes. Nearby plains show clays and sulfates, telltale signs of aqueous alteration. Put these pieces together and a picture emerges. A volcanic island where heat met water, where rocks leached chemicals into tidal pools, and where the very ground might have crackled with the kind of energy that sparks life. It's not proof, but it's a roadmap. Future missions could target these areas, drilling into lava deltas or scanning dried-up lagoons for molecular fossils. Yet the haunting question remains: how long did these islands last? On Earth, volcanic islands like Surtsey off Iceland emerge in explosive bursts, then erode or sink over millennia. Mars, lacking plate tectonics, might have preserved its islands indefinitely, but without active volcanism to replenish them, their fertile coasts would have eventually dried into deserts. That's the tragedy written into Elysium Mons slopes, a paradise that couldn't endure, an experiment in island biology cut short by a cooling core and a vanishing atmosphere. Still, the possibility lingers. If life ever gained a foothold on Mars, volcanic islands like this would have been prime real estate, sheltered, energy-rich, and bathed in water. Their fossilized remains might still hold echoes of that experiment, locked in rust-colored rocks that once knew the sea. And if we're right about what thrived there, even for a fleeting moment, it would mean islands aren't just Earth sanctuaries of uniqueness. They could be universal crucibles, scattered across the cosmos wherever fire meets water and mountains rise from the deep. At Mars' poles, vast ice caps gleam under the thin sunlight, frozen archives preserving billions of years of climate history in their delicate layers. Like Earth's Greenland and Antarctic ice sheets, these towering domes are nature's time machines, each stripe and band revealing ancient atmospheric secrets. But there's a twist. While Earth's ice is almost entirely water, Mars' caps are a surreal hybrid water ice interwoven with frozen carbon dioxide, creating a landscape where dry ice snowfalls blanket the ground and entire seasons vanish into thin air as the CO2 sublimates back into the atmosphere. This isn't just frost, it's a dynamic dance between two worlds, where Earth's familiar water cycle meets Mars' exotic carbon dioxide rhythms. The layered deposits at Mars' poles are masterpieces of planetary record-keeping. Picture slicing into these ices like a tree trunk. Each dark and light band corresponds to climatic shifts, with dustier layers marking stormier eras and clearer ice hinting at calmer periods. On Earth, scientists drill Antarctic ice cores to read past temperatures and CO2 levels trapped in bubbles. Mars layers tell a similar story, but with extraterrestrial flair, alternating bands of water ice and dust, some as thin as a hair, others meters thick, all sculpted by wobbles in the planet's orbit and tilt. These wobbles, called Milankovitch cycles, are cosmic metronomes dictating ice ages on both planets. But Mars' wild axial variations, up to 60 degrees compared to Earth's steady 23, make its climate swings far more dramatic. What makes Mars caps truly alien is their dry ice component. Earth's poles have frozen water and traces of other ices, but Mars grows literal CO2 glaciers that expand and shrink with the seasons. During winter, up to 30% of the planet's atmosphere freezes out onto the North Polar Cap, forming a meters-thick layer of dry ice. Come spring, this surreal frost vanishes without melting, sublimating directly back into gas, creating winds strong enough to carve the iconic spider terrain of radial troughs. It's a seasonal spectacle unseen on Earth, where the very air turns solid and then dissipates like a phantom. Yet beneath this dry ice veneer lies the real treasure: water. Mars' South Polar Cap hides enough water ice to drown the entire planet under 11 meters of ocean if melted. Some layers may be remnants of ancient snowfalls when Mars' atmosphere was thicker, while others could be the product of vapor diffusion water molecules hopping poleward over millennia. Radar scans reveal even more tantalizing hints: possible briny lakes buried under the South Polar ice, much like Antarctica's subglacial Lake Vostok. If confirmed, these could be the most habitable places on modern Mars, dark, liquid oases where microbial life might persist, shielded from radiation and fed by geothermal heat. The interplay between these two ices, water and CO2, paints a portrait of Mars as a world caught between states. During periods of high axial tilt, the poles warm enough that water ice migrates toward the equator, while CO2 dominates the caps. At lower tilts, water returns to the poles, potentially creating transient meltwater films. This delicate balance makes Mars' poles more than just ice repositories. They're climate engines, driving atmospheric pressure changes that may have periodically turned the planet more Earth-like. Some researchers speculate these cycles could have created brief, habitable windows throughout Mars' history, moments when the planet's freeze-dried deserts briefly bloomed with dampness. Earth's ice caps are vital climate stabilizers, reflecting sunlight and anchoring ocean currents. Mars' shrunken caps, though far smaller, play an equally crucial role. They're the planet's atmospheric regulators. When CO2 freezes out, air pressure drops globally. When it sublimates back, weather systems stir to life. This push and pull means Mars' poles don't just record climate history, they actively shape it, a feedback loop that's left the planet swinging between wetter past and arid present. For explorers, these icy layers are both archive and resource. Future astronauts could mine them for water or drill for climate clues like we do in Antarctica. But more profoundly, they remind us that even in the stark polar night, worlds whisper their histories if we know how to listen. And Mars' frozen story, written in twin scripts of water and carbon, may still hold chapters waiting to be read. These 24 alien terrains scattered across Mars aren't just geological curiosities, they're pieces of a planetary puzzle. each one revealing a different chapter in the story of a world that was once startlingly Earth-like. Taken together, they paint a portrait of Mars not as the barren wasteland we see today, but as a dynamic, water-rich planet with lakes, rivers, even vast oceans that might have persisted for millions of years. The implications are staggering. If Mars shared Earth's aquatic past, did it also share something even more profound, the conditions necessary for life to emerge? Look at the evidence written into these landscapes, from the dried-up river deltas of Eberswalda crater to the ghostly shorelines of Valles Marineris. These features weren't carved by fleeting floods or one-off events. They required sustained, stable liquid water, enough to shape canyons, deposit sediments, and create environments where chemistry could become biology. On Earth, where there's persistent water, life almost always finds a way. The same could have been true for Mars during its wetter epochs. The presence of minerals like hematite, clays, and sulfates, materials that typically form in watery, sometimes even habitable environments, only strengthens the case. But the real revelation lies in the diversity of these terrains. Mars didn't just have one type of watery environment, it had them all. Hydrothermal systems like those in Aram chaos could have served as underground incubators, fueled by heat and chemistry. The sprawling lakebeds of Jezero crater might have been calm, life-friendly oases, while the catastrophic flood channels of Casse Valles speak to moments of violent, planet-altering change. This variety is key. On Earth, life thrives in everything from acidic hot springs to frozen Antarctic lakes. If Mars offered a similar range of niches, it raises the tantalizing possibility that life could have gained a foothold in multiple places, adapting to different conditions just as it does here. Parallels to Earth's ocean floors are particularly telling. Submarine canyons, hydrothermal vents, abyssal plains, these aren't just superficial resemblances. They're evidence that the same fundamental forces shaped both worlds: gravity moving water, erosion carving rock, chemistry altering minerals. That shared geological language suggests something even more profound. The processes that make a planet habitable might be universal. If Earth and Mars, despite their differences, both developed river deltas, seabed-like dunes, and mineral deposits formed in liquid water, then the recipe for a life-friendly world could be written into the laws of physics themselves. Yet for all these clues, one glaring question remains. Where's the proof? Mineral signatures and eroded landforms can only take us so far. What scientists need now are smoking guns, actual fossils, chemical biosignatures, or better yet, living microbes eking out an existence in some hidden brine pocket. That's where future missions come in. Rovers like NASA Perseverance are already drilling into Martian rocks, caching samples that might one day reveal microscopic fossils. The European Space Agency's ExoMars rover, equipped with a deep drilling system, will hunt for organic molecules beneath the radiation-scorched surface. And then there's the dream of a sample return mission, where bits of Mars could be analyzed in Earth's labs with tools too bulky to send into space. The stakes couldn't be higher. If even a single one of these missions uncovers definitive evidence of past or present life on Mars, it would revolutionize our understanding of biology's place in the cosmos. Suddenly, life wouldn't be an earthly fluke, but a natural outcome wherever the right conditions persist. Mars would become exhibit in the case for a universe teeming with life, a world that tried and maybe even succeeded in sparking its own biosphere before circumstances turned against it. But even if the search comes up empty, these 24 terrains have already rewritten Martian history. They've shown us a world that was far from dead, a planet of tempestuous floods, tranquil lakes, and hidden oceans, where the same forces that shaped Earth's coasts and seafloors once worked their magic. And if Mars could go from that to the desert we see today, it carries a sobering lesson about how fragile habitable worlds can be. In studying these landscapes, we're not just uncovering the red planet's secrets. We're holding up a mirror to our own world, asking how long its oceans will last and whether one day Earth's own terrains might fade into fossils, waiting for some distant explorer to piece together the story of what was lost. From canyons to deltas, Mars landscapes whisper stories of a watery past, eerily echoing Earth's oceans. These 24 terrains aren't just geological curiosities, they're clues in humanity's greatest detective story, the search for life beyond Earth. As rovers and orbiters keep unraveling these enigmas, one thing is clear: Mars still holds secrets that could redefine our place in the cosmos. What do you think? Could these terrains prove Mars was once alive? Share your thoughts below, and don't forget to subscribe for more cosmic mysteries. But let's zoom out for a moment. These Martian landscapes aren't just scientific curiosities, they're mirrors reflecting our own planet's past and future. Consider this: the same forces that carved Valles Marineris and sculpted Jezero Crater once shaped Earth's Grand Canyon and Nile Delta. It's as if the universe ran the same experiment twice, tweaking the variables just enough to give us two wildly different outcomes. One world became a lush, living biosphere. The other froze into a desert, but not before leaving behind tantalizing hints of what might have been. That duality is what makes Mars so hauntingly compelling. Every dry riverbed and cracked mudflat is a reminder of how fragile a planet's habitability can be. Earth's oceans and atmospheres might seem eternal, but Mars teaches us they're anything but. Its landscapes are cosmic memento mori, whispering that even the bluest of worlds can fade to rust if conditions shift. And yet, buried in those same rocks might be the answer to one of humanity's oldest questions: are we alone? The search isn't just about Mars, it's about rewriting the story of life itself. If we find even microbial fossils in those ancient lake beds or hydrothermal vents, it would mean life isn't a fluke confined to Earth. It's a phenomenon as natural as planets forming around stars, a thread woven into the fabric of the universe. But if Mars turns out to be barren despite all its watery promise, that's equally profound. It would suggest habitable worlds might be rarer than we hoped, and Earth's vibrant biosphere even more precious. Right now, we're standing at a pivotal moment in this cosmic detective story. Missions like Perseverance and the upcoming Mars sample return are turning speculation into testable science. Every drill sample, every spectral scan brings us closer to knowing whether those rust-colored plains were once home to something alive. And with private ventures eyeing crewed missions, we might soon see humans walking those dried-up shorelines, searching for answers in the dust. So keep watching the skies and your screens. Because the next chapter of this story could drop any day in the form of a rover's discovery or a lab breakthrough. And when it does, it won't just change textbooks. It'll change how we see ourselves, our planet, and our place in the grand tapestry of the cosmos. Until then, the mystery remains. Mars keeps its secrets for now. But with every rock we analyze and every dune we map, we're getting closer to the truth. And who knows, the next clue might be hiding in plain sight, waiting for someone, maybe even you, to connect the dots. What's your take? Could those silent valleys and cracked basins hold proof of life? Or is Mars just a cautionary tale of a world that almost made it? Drop your theories in the comments, and if you've enjoyed this journey across alien landscapes, hit that subscribe button to join us for more deep dives into the universe's greatest puzzles. The cosmos is full of stories. We're just here to help.